Thank you for coming. It's a great pleasure to introduce Paul Fendley, who will talk about two cultures, mathematics and physics. And I think there's actually no better person in the world to give who understands these cultures so well, because every day Paul has to check all the papers that appear on the archive of mathematical physics to see whether they actually are conform the rules. Wow. So every paper that you ever submitted there, Paul has seen it. Anyway, Paul did his PhD with Paul Ginsparg in Harvard, and lots of postdocs, and arrived in Virginia, and is now a professor in All Souls. I think the most revered position in Oxford, because you don't have to teach. Yeah. But anyway.
Thank you, Frank, and thanks to the Institute. Thank you all for coming. Thanks to the organizers of the meeting. It's been fun. It's been really great to be here, and this is. So I just told Ulrika, yeah, I haven't given this talk before, but I've been, as you'll probably detect, I've been stewing about some of these things for many decades now. So I hope this is an opportunity to tell a story that in some versions gets told by many people, but I think I have a different way of saying it. So I don't know if you can read the cartoon, but that summarizes it a bit. So first the quote. So my title was Two Cultures Separated by a Common Language. The joke is mathematics and physics, but the original quote is probably due to George Bernard Shaw, but it actually doesn't exist in any of his writings, at least according to this marvelous website that investigates quotes. At least nobody's found it in any interview or writings. He was quoted, and all the quotes happened around the same time, so it's very plausible that he did say it, just wasn't recorded or printed directly. But there is something that this website dredged up, which I think is great. It's a much older quote by Oscar Wilde, where he says that in many respects she was quite English and was an excellent example of the fact that we really have everything in common with America nowadays, except the language. So literally it means exactly the opposite of this quote, but of course it means exactly the same thing. So, and mathematicians and physicists are, well, two different breeds, and that's what I'm going to talk about. So the first thing, okay, this language issue, and language is really important in the way we communicate with each other. And so I thought I was being clever. I found this quote due to Galileo, and then discovered that, well, in fact, lots of talks begin with this quote, because it is such a great quote. And so this is basically the first point where someone really says, to do good physics, he called it philosophy at that point, but he meant what we now call physics. You know, you need to do mathematics. And so this thing was, essay was where a lot of people say he's sort of the first person to write down what we now think of as the scientific method. But yeah, so the universe is this great book. Oops, sorry. How do we go backwards? There we go. I'll explain what that thing is in a second. The universe is written in that great book, which is ever before our eyes, but this book is written in mathematical language, and we can't understand any of it without this book. It's a really beautiful, elegant quote. Turns out in this book, though, at least according to Wikipedia, this book that has actually almost all the science in it is actually wrong. So he invented the scientific method, but didn't apply it so well. Another thing I found amusing, though, is if you look at this old painting, contemporary, I presume he sat for it, it says basically he's a mathematician in there. So in those days, those were viewed as the same thing. Anyone know what this is? This is, I said other talks have used this, but nobody used this bit. Anyone know what that is? Eric? So that's Galileo's middle finger. It's in a museum in Florence. You can see it. That's not my picture, but I have them somewhere. If you want to get students' attention, at least temporarily, when Galileo comes up, show them that. I don't know whose idea it was to chop off the poor man's middle finger after he died and preserved it, but there it is. Anyway, so maybe a more important question is why is mathematics so useful physics? There's a famous essay due to Wigner, the unreasonable effectiveness of mathematics and natural sciences. It depends on, I'm not sure, well, I agree with in a sense, you know, but I disagree with other. I don't think it's unreasonable knowing what we know now about the universe that, that mathematics is so useful for us physicists. And many phenomena in nature are universal. And so the simplest to explain example of this is, you know, when Newton did gravity, when he understood gravity, one of the key things that wasn't obvious at the time till he did his work was that it's the same. What makes Jupiter's moons go around Jupiter is the same as what makes us go around the sun, which is the same as when I drop something, it lands there. And that's not at all obvious why that should be if you're just looking at the phenomena. But nonetheless, it's true. And moreover, he then had a beautiful mathematical theory to describe it. And so the answer is, and so time and time again, we find rules that are both elegant and simple, and there is a well-defined mathematical sense. Most people here probably know what an analytic function is. And so we find again and again, we can accurately, extremely accurately describe nature via simple models and where the quantities are analytic, at least in some region of the parameter space in which we're studying them. And so, okay, so if it's unreasonable that that's true, then that's there. But given, if you take what I just said for granted, I don't think it's at all unreasonable that mathematics should play a fundamental role with physics. And we know in practice that understanding nature time and time again has led to deep results in mathematics. And this institute was named after probably the first person, well, one of the first people who did this. And Newton invented calculus, as we teach pretty well. He said it differently than we teach it now, but it's the same stuff. And he invented a quantified motion. And the question is, was he a mathematician or a physicist? I don't know or really care. Now, so, okay, a lot of water under the bridge since Newton, but in fact, people have recently asked even more interesting question. So, reverse to what Wigner said. Why is physics so useful for mathematics? So, like I said, physics has resulted in lots of mathematics, and you can see David Tongs on YouTube giving a talk with the same title as the Satia article. And people have even gone further. I'm not going to talk about this because I won't do it justice, but Tegmark and others have even to the point where they claim the universe we lived in is inherently mathematical, so all mathematics is part of the universe. I'll butcher the ideas I already have butchered the ideas. But at least people, not everybody, but at least people are thinking about turning this arrow the other way around. And so, yeah, so this egalitarian view where physics and mathematics are all part of the same story. Well, okay, maybe that was true in Newton's day, you might say, but it isn't now. So, yeah, so when doing this, so I found, I actually didn't know the origin of this phrase until I was preparing this talk, that mathematics is the handmaiden of sciences. This book was written by a mathematician you probably can't read in back. It says he was past president of the Mathematical Association of America. So a very evocative picture, to put it mildly. And then I guess he must have gotten grief from some of his mathematician buddies. So he wrote a book later that has mathematician both as queen and servant of science. All that, okay, just to set it clear, we both rule over you and serve you, which is really a remarkable thing. What's many things bizarre about looking at these things nowadays, this was, first one was in the 30s, second in the 50s, I think, but also is genderizing it, that mathematics in both of these titles is female, but also even weirder, his big hit book, the one I had heard of, I hadn't heard of these two, but predates these, Men of Mathematics. So it's a history of some of the great mathematicians, and so he's genderized it to, I guess, men do mathematics and mathematics is a woman. It's actually pretty weird when you think about it. Anyway, so we've divided, for whatever reasons, we've subdivided very much into two tribes. Most people that do this sort of research will call themselves one or the other, at least roughly. You can say one tribe, the mathematicians prove things rigorously. The other tribe, theoretical physicists, try and understand things through other methods. And so there's a lot of invective that's come out over the years. So I'm not going to make the talk about invective, but I had to do one slide. I'll probably backslide and do a little bit more. One slide featuring my favorite insults from the field. So I couldn't decide which order, but I went with maths first. So here's one. Very little mathematics is useful practically, and that little is comparatively dull. So anyone know who said that? Said, what? Yeah, very good. Okay, yeah. Right, so Cambridge mathematician, by the way, wrote this bizarre book in the, of all the things I looked at for this talk, this was the weirdest one. I read it long ago, but I couldn't even read it. I just cherry picked this quote. It's just a strange book. But anyway, it's called A Mathematician's Apology. It's a very strange book. All right, so this one, well, it's a pretty good insult. Throughout mathematics inspiration, the hard work of completing proofs are necessary. Throughout mathematics, not just in what I do, in all of mathematics. And no guide from physics can help. Fighting words. And then another one, sounds a little bit more reasonable, but I think it's equally wrong. Theoretical work, and they very much meant the kinds of work that physicists do, or mathematicians backsliding, should be explicitly acknowledged as theoretical and complete, and particular, a major share of credit for the final result must be reserved for the rigorous work that validates it. Notice the word, not even just the word rigor, validates it. It's not correct until a mathematician has stamped it. So those are fighting words, and these say physicists aren't shy. So then some choice quotes there we're talking here about theoretical physics, and therefore, of course, mathematical rigor is irrelevant and even more so impossible. So not just irrelevant, you can't do it. And then this mathematics is the hand made into physics, but I first heard it from Shelley Glashow, who was most definitely not doing it to say how awesome mathematics is. And the two bottom quotes are actually the ones that bother me the most. I'm going to return to that one later on, or to this Jaffe and Quinn paper that said it all. I'll say more about it next. But then this other one actually bothers me quite a bit because it says, okay, so this is from a text by Condon and Shortley, and it's an introduction where they're trying to explain why they don't use group theory to do what they're doing. This was a textbook called The Theory of Atomic Spectra. It's written in the 30s, but people were still talking about it and using it in the 80s when I was a grad student. And they basically sniff at the beginning. They're basically do a long, weird explanation of why they're not going to use group theory, because who needs, we can do it without it. And then they make this statement, if we can minimize the amount of mathematics a physicist must learn in order to penetrate a new field, we do him a real service. And that attitude pervades physics, and it's bad for those physicists there who learned this thing in quantum mechanics called the Wigner-Eckhart theorem. It's a completely trivial consequence of group theory. But if you look at a standard quantum mechanics textbook, it's presented in this bizarre, incomprehensible way. So anyway, this kind of attitude did real damage in the education of young people. So, and speaking of the damage, or purported damage to the education of young people, so this Jaffe and Quinn quote that I had at the bottom of the math side of the last page came out of a paper that was a big deal at the time for people talking about math. At least I don't know if people, has anybody heard of this paper now? Who wasn't around at the time? Anyone know this? Okay, one, yeah. Well, only one person at least admits to knowing. Yes, it was a big deal. So it came out in '93. And I know I know some of the reasons that motivated them to write it. Which I'm not going to say in public, but you can ask me over a drink. And so what it was is they were bothered by lots of physics coming into maths. And so then they wrote this article. The article was very professional, and they were trying to be reasonable. It wasn't a polemic, but it's hard to, at least now, or at least at the time, even at the time, I take it as anything else. I mean, when they begin their abstract, is speculative mathematics dangerous? They meant physicists doing maths or mathematicians doing things without proving them. Or I should say, mathematicians doing things without writing down the proofs. And then, you know, so speculation is the fabric of theoretical physicists. So that's all people like me do. We just speculate. And this, of course, can have unpleasant and destructive consequences. I said Condit and Shortley was bad for physics, but I'm not sure I would have gone quite as far as this language. Anyway, serious caution is required. But then what they do is, so they're trying to be positive, is they say, oh, well, okay, here's the role. But they then basically set out rules to put people like me in our place, you know, meaning people who don't write papers with theorems in them. And they set rules. So we're not allowed to say show. We can't show anything is true. We have to say predict. And we even have to flag this in the title with theoretical, speculative, or conjectural, maybe color coding, I forget. So it was a bit strange. Now there's a whole big story on that. I'm going to come back to it later. There were lots of responses. I think in the end, writing this thing was actually ended up being a good thing because it got a lot of interesting discussion. All right, so the central point of what I'm going to talk about, well, and I'll give an example to try and illustrate what I'm saying, is that there's really no meaningful dividing line between maths and theoretical physics. I hope that statement at least doesn't sound controversial. And obviously, like I said, we're two tribes. We often do things in different ways, but there's really no good way. And I think, I mean, you know, Jaffe and Quinn are hardly the first people to say things like, I just singled out. Anyway, luckily, you know, people have ignored this. I still use the word show, so sue me. I don't call what I do speculative. Actually, some mathematicians have read some of my papers, and I don't think that they've been damaged. I think. They seem okay to me. They didn't get fired at any rate. And sometimes, by the way, they use results from physics, occasionally mine, and they prove interesting theorems. So they benefited by talking to such low life. Sometimes physicists, actually something that maybe not appreciated, sometimes physicists derive results that are theorems. We just don't write them that way, and I'll give an example later on in the talk of such a thing. Now, sometimes if you do look at the literature, they do use the word prediction when they're referring to a physics result that they've proved. So that one maybe I don't like, but the other four things I think would be fairly non-controversial statements, and I'm okay with those. All right, so to make a silly analogy, but just to belabor the point slightly, so the physicists have all seen this diagram, but there are some mathematicians here, so go there. This is the phase diagram of water, where this axis is pressure, and this axis is temperature, but you can't read it. And so basically, the lower the temperature, you make something solid, and you raise the pressure. You might think, well, you go from a gas to solid. You compress the water vapor around us, and eventually it becomes liquid water. Lots of interesting things about this diagram, but the interesting thing is gas and liquid are indistinguishable. Now you say this is crazy, I can tell the difference. And indeed, when you're at our pressure and our temperature, so this is atmospheric pressure, and well, I guess 0C is in here. You know, when you're where we are today, that's here. And yeah, so to go through what this line means, it's a phase transition. You have to actually put energy into the liquid to boil it or put more pressure. So you either have to raise the temperature or increase the pressure to go from liquid to a gas. Go from gas to a liquid. I think I said them backwards, but you know what I mean. But the thing is, you follow this line. So this is an enormous pressure. This is something like 200 times atmospheric pressure, and pretty hot, but not, I mean, not crazy hotter than your oven. So 370 or something centigrade. This transition stops, and there's no way to get from there to there. So I think it's actually a pretty good analogy. So fine, you know, most of us are living in the mathematical or physics world somewhere along here, and there's a clear difference. But if you keep going around here, you can move around with that, and you can't tell. There's no difference between liquid and gas. So here, let me give a few. This is a wisecrack, my calling this a proof, but let me give a couple quick arguments. Obviously, lots of what I just said, I think lots of great mathematicians and physicists would agree with me. Lots of great mathematicians and physicists probably disagree with me, but at least some have. One who definitely spoke out many times about this was Michael Atiyah. He had this lovely thing in this paper, which he called The Unreasonable Effectiveness in Physics and Mathematics. This was a talk, so he did not actually make this for a figure, for a genuine paper. Somebody transcribed his talk. But it's a timeline of maths and physics over the century, over the 20th century. And so back to t equals minus infinity, I guess, it was maths and physics were the same. But somewhere around 1940-ish, in his opinion, math and physics split, but then, in his opinion, they came back together in the 70s. He didn't really say in this article what happened around then to split them. I can guess. Bourbaki being one word. I don't know if anyone has any other thoughts as to what the split made. But anyway, but in his opinion, at least, it came back together, and there's he gives lots of examples of why he thinks this. Another one that I really like is from this book called What is Mathematics by Courant and Robbins from 1941. And in the introduction, so one thing I should say, the quotes I'm going to give are much more, except for those schoolyard insults by the physicists, they're almost always by mathematicians, because physics tend to not think about this, and when they do, most of the time what they say is not very good. It's a schoolyard insult. Mathematicians spend a lot of time thinking about this. So you can say that's, to me, one characteristic. You're a mathematician if you like thinking about stuff like this. Maybe that makes me a mathematician. Anyway, so in this book where they're trying to address what mathematics is, they say seems to be a great danger in the prevailing overemphasis on the deductional postulational character of mathematics. I mean, proof, axiom, the axiom theorem proof. But I love this little bit here. Only under the discipline of responsibility to the organic whole can the free mind achieve results of scientific value. So I really like that. In particular, I like the organic whole as a way to think about science. And unless you think there's an out of scientific value, say, but what's the value of mathematics? In the same paragraph, or on the same page at least, as this comment, they very clearly mean by mathematics. In fact, they say, if all you're interested in deductional postulations, then no reasonable person no intelligent person would be a mathematician if that's all mathematicians did, which I thought were fighting words, but I quoted that. But I didn't write it down. Now, a bizarre thing in the thing that I noticed when looking for a cover, so this isn't even quite the original cover of the book. I think I have one, but I left it at home. But so this, I think, is the original picture on the cover, which looks kind of dense and nasty and all that. The font looks like a 60s font, so I think this is the original photo, but a different font to the original cover. But then when the book was reissued in the 90s, that's the cover, and you're like, ew, clouds and numbers? This is the best their graphic designer could do for what is mathematics. Okay, they put in very small font, an actual formula, not even a really interesting one. Anyway, so I don't know. That I think says quite a bit about where we are as a discipline. All right, so now since I'm a physicist and physicists like to do certain things. And one of the physicists' things to do is what drives mathematicians crazy, and it's sort of give an example of what you're talking about, and then act as if now we've established the whole thing. Put aside whether this is a good idea or not. I think it's at least good pedagogically, and for a talk like this, I think I want to do it pedagogically. So I'm going to do that, and I'm going to give you an example that I hope really illustrates this point that physics and math are pretty hard to separate what's what. And this, again, this organic whole that I like very much. Maybe, hopefully will illustrate this, so it's not a proof. All right, so let me ask a question that is, I don't know, I guess it's a math question. And how many ways is there to take 32 dominoes and then, so that's a domino, and so 64 squares on a chessboard, my domino covers 2 of the squares, and how many ways are there to arrange them to cover the chessboard? So I keep putting them down and all that, and then I cover the whole chessboard. There's obviously a lot, because you can take this random one I did, and then I can then sort of flip these to, you can do lots and lots of things. You don't have to say, because people don't like being embarrassed, but make a mental guess of how many there are. I'm going to tell you the answer soon, but see if you can guess. Anyway, so before I tell you the answer, though, I say, well, why? Okay, it's a cute counting problem. Mathematicians like cute counting problems, but why this cute counting problem? And then why would a physicist like me be interested in this cute counting problem? And the reason is the following. So there has a name in the fields. Mathematicians call this a perfect matching. You're matching the adjacent points. And physicists would call this a Dimer cover, and I'll use that language. And so this is just an abstract version of what I had on the previous slide. Each dot represents one of the squares on the chessboard, and the line represents the domino going between 2 of the squares. And so this is one configuration. I guess I should have made it 8 by 8, so it would be a chessboard, but it looks like it's 6 by something, 9, whatever. But this problem, actually, I'm going to give you a quantum physics version in a few minutes. But for example, if you're dropping diatomic molecules on a surface and then they adhere in a certain way, this is the counting the ways, what's called the entropy. And so this is an experimentally relevant thing you might want to know. But the real reason, to be honest, for me, and this is a case where mathematicians are much more honest about it than physicists, is why we're interested in this problem is because we can solve it. And there's some, I'll explain momentarily. I do. So this is the number. There's nearly 13 million of them. I mean, obviously nowadays you could have a computer count them, but what Castelline, Temperley, and Fisher did was derive a way to actually compute this number. So I'm going to try and tell you about this next. All right. So these are the papers. Their work is rigorous. They didn't write it that way, but their work is rigorous. They give a formula for this thing. That's the answer. I mean, there's no more. You can try and prove it in a different way. All that. These are the 2 first papers. They actually they solve. You can see on a quadratic lattice. So they solved special cases in this. It was a paper by Castelline later in the 60s where he did it for an arbitrary planar lattice. And I think the result is just beautiful. So I thought, okay, I'm going to try and explain how they did it, or what they did. I'll explain the result. But before that, I want to point out one thing. Okay, so these are physicists, but they have a beautiful, rigorous mathematical result. But you might notice if their institutional affiliations here are not exactly known mathematical institutions. One was, if you can read in the back, that's Shell Oil Company research thing. And Temperley was at the Atomic Weapons Establishment. And so all these places obviously are interested in math, but let's just say the purity of math was probably not the concern. And only Michael Fisher was at a standard physics institution. Anyway, one thing warning, Frank showed me this morning, which he got from someone I better not name in case they're embarrassed by it. But anyway, so I am going to write down a matrix, and I learned only this morning by Frank in the Bourbaki school. They view matrices as being preposterous. The Bourbaki books were famous for having no figures, because somehow figures were bad for a mathematical soul. I mean, this was the insanity of I think, I'm not putting words into his mouth, but I would guess that he was thinking about when do this. So warning, if you're offended by my using a matrix, well, sorry. Anyway, so back to these papers, and let me explain one slide what the result is. It's really marvelous. Okay, so you make a matrix, the dreaded, the preposterous matrix. And so each site on your lattice, and actually you can do this for any planar graph, so each vertex on this planar graph labels one row or column. So for the chessboard, you would have a 64 by 64 matrix. Okay, and then to populate this matrix, you make a rule. So if the two sites, which remember are labeling the entries, J and K, if the two sites are adjacent by whatever you've decided this graph is, then the entry is either 1 or -1. So now the tricky part is putting the sign. Sorry, and it's 0 if the two are adjacent. So it's a very simple matrix, now called the Castellan matrix. And the rule's a little tricky. It's basically you have to orient the lattice such that you go around in an even length cycle, and you always hit an even number of. You always hit an even number. Sorry, an odd number on an even length cycle of these arrows when you put the arrows on the length. So that's the one subtle part. And that's what it took them 5 years or so to figure out how to do this. Okay, so let's do this for a super simple case. So let's just take a very simple sites. This we can do in our head. So it's got four sites. I'm going to ask how many different ways of covering this lattice with dimers. So obviously the answer is 2, but anyway, but let's do the calculation. All right, so you orient this lattice in this way. So I put arrows on it, and you go around the one cycle of this lattice, and you hit an odd number. You go an odd number of forward arrows, and because it's even length, you go either direction, and it's odd. Okay, so the result is now you write down this matrix such that if basically it's a forward arrow, then you put a 1, and if it's a backward arrow, you put a -1. So that necessarily makes it an anti-symmetric matrix or skew-symmetric matrix. So, for example, the first site, both the arrows are pointing out, so that's why in this row it's 1, and in that column it's -1, and so forth. So that's the matrix. That's the Castellan matrix for that thing. And then the result is stunningly beautiful, which is the number of dimer coverings is the square root of this determinant. That's all. So sure enough, you take the determinant of that. I worked it out, I checked, it's 4, so the square root is 2, and those are the 2 dimer coverings. But of course, this works for the chessboard, and it works for any planar graph. So you can prove that this prescription, you can always do this, and that it gives the correct answer for a planar graph. So that's pretty neat. So now I said a few minutes ago, this is actually of interest in quantum physics. And so there's a question you can ask, and people started asking this, 30 years ago or so. Now we can make a quantum system of dimers. And so there's a long story with that I won't get into. But basically, so you have the lowest, at the end of the day, you can arrange it so the lowest energy state of this quantum system is comprised of a superposition of all states that you can label by these dimers. In the actual quantum system, what this is a pair of entangled electrons. For the physicists in the audience, this is suspense-synchron, or this is sometimes called a valence bond. This superposition is called a resonating valence bond. Anderson, he of the nasty crack in the earlier slide, is the one who first thought of this, and while he was a professor at Cambridge, actually. He was at Cambridge for some years in the late 60s, early 70s. Rothschild and Kibelson then revived the idea beautifully in circa 1990. Okay, so now we want to ask a physics question, which is this deconfined? And so what that means is, okay, if we put some energy in and we break apart one of these bonds, in a physics language, you make it, there's no longer in a spin singlet state. So we break apart this thing and then we move them apart, and then we try and ask the question, does it take larger and larger amounts of energy to push them farther apart? And the physicists like this word. This is confinement. You may have heard of this in the strong interactions, what holds a nucleus together. The proton is made of quarks, but if you try and do this, they're confined. You take arbitrarily large amount of energy to pull them further and further apart. So that's why you never see free quarks. So this is a much simpler model, but it's the same question. Can I pull these holes, we just pull out those electrons, break the bonds, and just throw away those electrons. And can you do it? And point is, now this calculation is reduced to the calculation that Castelline, Temperley, and Fisher explained how to do. Because poking out a few holes in here, so there's my hole and there's the other one, it's like at locations J and K, is still a planar graph, so all the stuff they did applies. And so then the number that gives you a measure of the confinement, well, it tells you if it goes, is just take the ratio of the number of coverings with the holes over the number of coverings without the holes. And so in this simple example I gave, well, if I put the holes here and here, there's one way to color it. There's two ways without any holes. But if I put them here and here, the holes, then there's actually no way to do it. So that's a computation. But and then the physics of this is, we say the holes are confined as if there's basically the zero probability to drag them apart. They'd be confined in this quantum theory, and they're deconfined if that number R approaches a constant value as you drag them very far apart. So Fisher and Stevenson had done this calculation very long ago using these techniques that Fisher and the others developed, and they found that it does go to zero. For the experts, it actually goes to zero algebraically, which is interesting, but it does go to zero. So it's confinement. And we're math intersecting the story. So it's rigorous in a finite lattice, but they want to take a limit. So you take the holes very far apart, and you then have to take the lattice very far apart. But there was a theorem already known at that point called Zago's theorem. And it tells you things about the determinant of Toeplitz matrices. And they managed to, which this turns out to be. So it gave the rigorous answer, at least in enough cases so that has established this result. Okay, so that was, okay, so that's one story. So what Rothschild and Kibelson were talking about the square lattice, so their work was then circa 1990, and that was forgotten, but things came up again. So people in condensed matter type systems started thinking about issues of confinement. There's a super famous paper by Alexei Kitaev on a model now called the toric code. And one of the key things about that model is the analogs of the holes in this case are confined. That paper, so then there was another paper a little after, but when they wrote their paper, Kitaev's paper wasn't well known yet. It took a while. And Messner and Sonby in this beautiful paper said, well, if you change the lattice, instead of doing the square lattice, do the triangular lattice, then they are deconfined. And this has some really interesting physical consequences. It's what people call now a spin liquid. Don't ask me to define that. I would say it's a liquid that has this kind of deconfinement. So a very circular thing. But it is an example of something called spin charge separation. And it would take me 5 minutes to explain what I mean by that, but if you want to know what that means, it's something very interesting. I'll explain it in the questions. And the difference is, the key difference is between the two lattices that you might already know. Triangular is not bipartite. So what bipartite means, like with the square lattice, you can color each of, well, the squares, the vertices, in this case, with two colors without them touching. It doesn't count when they touch at a point. So, and it's really curious. Until Messer and Sandi wrote their paper, Messer and Sandi, it was never written in the literature that this was true, but they asked a bunch of experts. I knew some experts that they didn't know and asked them, and all the experts on dimers knew this, and nobody ever wrote it up because nobody thought it was very interesting. Only when the physicists came along, certain quantum physicists came along, did they just, well, then all of a sudden it got interesting. So then we can now try and quantify this. How strongly are they deconfined? And so we define the same thing I defined for the square lattice before, but now it's going to give a non-zero value. So again, I take the thing, I remove two of these electrons, poke them out, and then ask this thing how this ratio of the number of coverings with the holes over the number of one. So for giving you an example a little more on this, so if you look for a nearest neighbor one and then make the graph super big, it's going to be roughly 1/6 because it won't feel the boundaries. And so thus, there's a 1 in 6 chance that this one will be connected to that. So we did this calculation, so I had to do something with my involvement in this. And so we got an answer. Again, it's rigorous in finite size, but we get the determinant of a pretty nasty matrix. For those of you who know something about matrices, it's a Toeplitz plus Hankel matrix. Toeplitz are matrices where the entries are the same all in one direction. I guess, sorry, from your point of view, this direction. A Hankel matrix is the one, all the entries are the same along the diagonals going this way. Toeplitz plus Hankel, it's the sum of the two. So the Zagos theorem, the one that works beautifully for the square lattice, isn't obviously useful here. So I was kind of annoyed by that fact. So one afternoon, we had these nice expressions, and so I set the computer a-running, and I, got this number, which is answer. And so I think I had even 40 digits. It took a couple hours in 2003. So presumably on Frank's watch, you could do, or Frank's phone, we could do 50 digits in a few minutes. Anyway, so you find it's very deconfined. So it's 1/6 for nearest neighbors, and far away it's almost 1.5. So the holes really are not happy to run far away from each other, which is pretty interesting. Okay, so, all right, so there's this number, but then, all right, this was unsatisfactory because, there's theorems and all that. So, all right, so there's that number. So I gave a talk on this in Illinois. And there was this wonderful mathematical physicist, Mike Stone, in the audience. And Mike goes to me, so I showed that number. And Mike said, did you use the inverse symbolic calculator? And of course I said, Mike, what is the inverse symbolic calculator? And he says, you plug it in a number, a fixed point number, floating point number like this, and it spits out to you if it's the combination of some interesting constants, maybe some special value of a digamma function or whatever. So of course after the talk, we go back to Mike's office and we plug it into this, and there we go. And that's the number. Even to all 40, even though digits I didn't include. Yesterday, I went and looked to give you the web address. I couldn't find any operating version of it. So if you know anybody involved in this, please beg them to put it back up. Well, having said this, over the years, both Roderick Messner, who co-wrote this paper with, and I, every time we had a constant, in some calculation, we'd always go and plug it in. Neither of us ever had this result ever again. So maybe the fact that it doesn't work anymore will save me time. Anyway, but it's so cute, so marvelous. All right, so at this point, so I, believe it or not, I have mathematician friends. Maybe, hopefully I still have them after this talk. And so I told this result to Craig Tracy, who's one of my friends. And he said, oh, in fact, one of my collaborators is an expert on this Topless plus Hankel. I didn't even know Hankel at that point. He's the one who told me that's what they're called. Estelle Baser, and so we had this nice thing. She goes, yeah, well, the result is known, but it's written in an abstract form. And again, I don't understand mathematicians. I'm not sure what it means when a number is a number and an abstract form is not, so I'm not sure what it means by known, but it was known in some, at least in principle, they could do it. And I think it was a considerable amount of work, but they did compute it, but in fact, they did something, they extended the results. So we had in our paper, for physics reasons and also because it's kind of interesting, generalized the calculation I just described. So we included a quantity which I like to call triangulosity. It's a word I invented. No one else other than me on this planet has ever used it, but I'm still desperately trying. So what triangulosity means is the following. Okay, you start with the square lattice, so that's the square lattice, and then you would be putting dimers on the edges of this lattice. But then you can make a triangular lattice, if you wish, from the square lattice by putting things on these, putting extra edges on these diagonals. And you can even then assign a probability, like instead of giving it probability 1 for each edge, you give it a probability t for each of these triangulars. So you can continuously interpolate in this counting problem. Well, it becomes a probabilistic problem between square and triangular. And anyway, so Estelle and her collaborator came up with this marvelous formula, which we had these awful matrices, but and that's a weird answer, but it's not a bad one. Still to this day, so I don't know a good physics proof of this. I mean, come on, this is simple enough. You would think there should be some more direct way of getting this without, I mean, what they do is a very intricate analysis. People still study determinants of Topless plus Hankel matrices. So anyway, I said, obviously I don't like having my livelihood called speculation, and so I hope this example illustrated that, well, I don't think why that's so. And, so first, the story started way back in the early 60s, this beautiful work of Castelline, Temperley, and Fisher. So not only is it rigorous, but it ended up inspiring a huge amount of both physics and mathematics. If people, there's things by Kenyon, Sheffield, and Akunkov and anyway, all this amazing stuff, in both fields. Then Fisher and Stevenson pushed it farther, computing this deconfinement thing, and had to use mathematics to do this. Then it turned out to really have a nice application in condensed matter physics, or quantum condensed matter physics, and really clarified conceptually a lot of important issues. And then my small part in the saga, we did this thing with tantalizingly close to simple, and then the mathematicians came back in and not only proved this simple bit, but then they managed to come up with something even more general and more elegant. So, I hope that too. So, okay, so there's lots of possible things you can complain about. So this one I thought maybe a little bit amusing. Okay, so one thing people say, I'm as Frank said at the beginning, I moderate on archive, and one of the things I've heard said, well, you can tell a math paper because it's written as theorem proof. Well, okay, so I mentioned before these beautiful dimer papers weren't written as theorem proof. But anyway, I thought, all right, well, we live in a different era than 1960. So I thought, what I'm going to do, I'm going to plug in our paper, the one I wrote with Messner and Sandi. I'm going to plug it into ChatGPT and ask it to make it theorem proof. Well, don't read it carefully. It's total crap. But it looks like theorem proof. And if you're moderating on archive, I think you wouldn't tell the difference. So, it's not a real maths paper. Our result, well, actually, these theorems are not rigorous. There's stuff earlier in the paper that was rigorous, but ChatGPT didn't understand that. And this is, it's a bit of a wisecrack, but it's not, because, mathematicians have this venerable tradition of, we really referee our papers, physicists don't. The latter is certainly true. But it's really easy to generate crap like this. Archive has seen this huge spike in recent months of ChatGPT generated stuff. And the easy stuff you can tell if it has Riemann hypothesis in it or a Navier-Stokes, an automated thing. But what's happening also is people who are legit, but then doing things that are outside their expertise are using ChatGPT to then help them extend their work. And it's a real nightmare. So I think very, very significantly, I wouldn't use form over content as a defense of the division between the two fields, put it that way. All right, and another small thing I want to mention, in physics, this one isn't, I think, discussed a lot. It does come up a bit in all the stuff I read. But physicists sometimes come up with exact results. And so obviously sometimes physicists do proximate things. But for a given well-defined mathematical system, we do our things, and we come up with an exact result. What I described before is sort of an example of this, but even better ones are with critical exponents. And the point is, you can then, so the physics prediction, if you want to use that word, is an exact number, 1/8, 4/3. And so the method to derive it may not be rigorous, but usually what the complication is because they do some calculation in some setting and you need to then take some limit for it to be true. Well, if a number is always 1/8, obviously the limit is going to be 1/8. You just have to prove that the physical system is converging to whatever you want to believe it's converging to. But my point is that if you have this number, and then you can check it in other ways. Now, if you screwed up, if whatever physics thing you did was wrong, well then the real answer won't be 1/8. It'll be 14, and then there's no particular reason you would see anything close to 1/8. And in the example I gave, look, it was 30 digits to that root of a root. So I mean, I think that's a pretty likely indication that what you're seeing is the truth. And so it doesn't prove it, but I mean, again, I think that's more than speculation. And Arthur, I'm going to go back to Jaffe and Quinn to close out. But then, I should say, I've never met Frank Quinn of the paper I was complaining about before. I've met Arthur Jaffe many times, known him for a long time. And he's an absolutely lovely man. And this is the last time I saw him, he gave me his card. And, has on here, beauty and truth. And I think we're actually, even though we may disagree on some of these things. I was too scared to ask him if he still believes what they wrote 30 years ago. Maybe next time. Now that I'm out in public on this, maybe I'll ask. Maybe next time I'll ask him. All right, so let me just to close out, let me go back to some quotes. So I mentioned, this Jaffe Quinn really, even though it's been forgotten, I think it was really good, and I think it really formed. There are a bunch of people they're on archive, both Jaffe and Quinn's, and the responses are, with one exception, bundled into one paper, so you can quickly look. I mean, many are really good, some aren't, some are weird. I learned a famous mathematician wrote something, I think, like a modest proposal. I think it was this bizarre thing. I mean, talk about rigor mortis, rigor as in mortis. That was bizarre and funny. But I'll close with the couple of what I think the better ones is. I mean, point is, it's just Karen Olenbeck's quote is it's just kind of silly to try and make these barriers. I mean, what good is it? I mean, the usual thing is, the young will be corrupted, but do people really believe that? So I think that's really a nice quote. Then there was a long response. This is a separate archive thing because Thurston wrote a very long, and in part because he was really taken to task in this article because he had this famous geometrization conjecture. He proved it for some cases, but never really finished writing up the proof. And so they singled this out as bad mathematical behavior. And he wrote this long thing, which is really great. I recommend anybody to read it, both about his own career, but it makes a bunch of good points. One is that, he analyzes the motivation he points out, I think correctly, that Jeffy and Quinn, basically, it's all weird. Oh, who gets credit for the theorems? That quote I used before, the theorem, that gets the credits, screw the physicists. And so that's bad for us physicists, obviously, but he points out that's bad for mathematics because his big point is our job, or at least he's saying as a mathematician's job, is to advance human understanding of mathematics. He says that's a bit circular, but then he tries very hard to explain what he means by that. And that in this endeavor, much better off recognizing and valuing a far broader range of activity. And certainly I can't say it that well. And I might add, this thing, absolutely 100%. So I said I'm using quotes from mathematicians because they wrote a lot more about this, but absolutely everything in this quote, I think, just omit the theorem credits. I think in physics you would say direct relation to experiment or something like that. When I was a junior faculty member, the department chair would like to thunder at every conceivable opportunity. Physics is an experimental science. Yeah, looking at me. To put we theorists in our place. So we get it from both the mathematicians and the experimentalists. It's a tough life for you, the theoretical physicist. But anyway, so that attitude is hardly there. So again, physicists I think could go with Thurston's moral pretty well. All right, good. I actually timed this pretty well. All right, the real thing is, in this another quote from Grant Robbins, this What is Mathematics book, and this is Neil Young, take my advice, don't listen to me, and this is what they say, fortunately, creative minds forget dogmatic philosophical beliefs whenever adherence to them would impede constructive engagement. I think a modern version of that I like is, you do you, babe. But anyway, a more serious, I'll just read it. Anyway, thank you very much.
Thank you, Paul, for this beautiful lecture. Are there any comments?
I think there's now an online encyclopedia of integer sequences.
Yeah. No, that's amazing too.
I don't know if it has this one.
No. So that one you have a series, 1, 7, 11.
Yeah,
I've gotten multiple papers out of that one, but this one takes this floating with this decimal number and you just put in as many digits as you know, and then even when it worked, it gave you a table, so you could see where your number fit in.
Right. I think this one also has decimal sequences, though.
Is what?
The one I mentioned, it also has decimal sequences.
Oh, does it? Okay.
It does.
I just Googled it last night and I found the old addresses, both, which I remember using in V1.0 and then we can.
You can try putting it in this.
Yeah, okay. Well, if anyone finds this working, please send me the link so I can correct this. It's fantastic. It's really cute. So.
Triangulosity is the same as triangularity.
Is it? Is that word used?
No, I'm just asking.
I don't know. It's a good question. I don't know that word either. So maybe I've just.
No, we have an adjective triangular, right?
Yeah, such triangularity. Yeah, but I specifically wanted to mean this way of interpolating.
Triangles, we have such one problem.
Yeah, no, it's a triangularity would work too. Well, nobody. I don't even think my collaborators let me use it in the paper, so it's only in talks that I can try to think, okay, triangular. Yeah, maybe that would have caught on if I had used that one instead.
Are there any cautionary tales of physics that's been turned into kind of physics conjectures that have been made into rigorous conjectures which have turned out to be false, which I guess would be a kind of a good example of
being
physicists.
Seduced by...
I mean, obviously, there are lots of examples of when it's all worked out.
Yeah. There's lots, of course, that haven't been proved. It depends on what you mean, of course. Yeah. There's certainly lots of physics things that mathematicians took seriously, and then, of course, didn't go. But yeah, but you said formalized into some really
like,
meaningful.
For example, you write critical experiment or something like
Yeah.
that.
I think those always work. Yeah, I mean, Duminal Copan got a Fields Medal for doing exactly this, and at least if he found, I mean, it wouldn't be in his interest to write a paper saying, "Oh, this one doesn't work." But multiple cases of these, and including some really, ones that I never would have expected, to be proved. So there must be examples, but no, that's a good thing. A cautionary tale. Well, poor mathematicians were led astray by the siren call of physicists. No, okay, well, good. If anyone comes up with examples, if anyone ever lets me give this talk again, I can then say, all right, here's a place where mathematicians were led horribly astray by physicists.
I was actually surprised that you didn't talk about string theory. Why not?
Yeah, I thought about it. Let's just save that one for the drinks. Anyway, yeah, there's a lot to say there. I mean, obviously the interaction that Atiyah was mostly thinking of was the many fantastic things that came out of the interaction in geometry and physics. But I suspect people have heard at least some of that story. I was going to do a bit on Seiberg-Witten and decided just because I had enough other stuff to say. But no, and there's a whole other sociology of that thing. But anyway.
We want to maybe set up a new journal. We'll call it Journal of Intermediate Rigor or something.
That's not a bad idea. Yeah. No, it's
Okay, that was a joke name, but
yeah.
some sort of in test high quality results, which are both, in both of the types formal proof and also this, let's call it prediction conjecture kind of thing. I guess in mathematics usually you only expect a high rigor. In physics you do not expect a formal proof.
Yeah.
So maybe if there is something that can combine the two, I won't have to hesitate when I'm submitting to one of the.
No, I think it's a great point. No, because I rarely know where to send my papers. I mean, sometimes I write physics, but I write with physicists. So if I write a paper with a physicist, there's some physics stuff in there, so it's there. If I write a paper, with a mathematician, which I have occasionally, then then it's theorem proof, and it goes there. But yeah, no, in fact, there's my most well-cited paper of recent years hasn't been published, and part of it is because I have no idea where. I mean, I could get it published, but haven't bothered. Yeah, so okay, that could be the first paper of the Journal of Intermediate. I like Intermediate. That's a good name, though. I like that. Yeah.
So, with proofs or with experiment, sort of obvious to decide, I guess, is this good work?
Yeah.
But if it's not a proof and it's not directly related to experiment, how do we decide if it's good or not?
No, that's a huge problem.
Who decides?
You've hit the issue with string theory that I wanted to avoid in this. And that's hard. I mean, it's a real, I just ducked it. It's extremely important. And in defense of some of the things Jaffe and Quinn, I think that's one of the things that culture, and that, they were in the 90s, and so the big early phase of string theory had happened. The excitement had then worn off by 93 when they wrote it. So they were very much sort of reacting, okay, where are we now? And, these string theorists go around writing all these papers, and they're not math, and they're not physics, and what are they? There's lots to say, but I just ducked it. And it's a real issue, yeah. So for the Journal of Intermediate Rigor, I think you have to say, you need a concrete result. You need a form. I mean, you need a precise statement. I mean, okay. I'll give the 10-second version. The key thing missing from bad papers, I think, is precise statements. And so I don't care so much whether they're rigorous or not, but I care whether they're precise. And that's a justifiable criticism against many physics papers, probably including some of my own.
I wanted to comment that there is a journal called Experiment in Mathematics.
Yes, so sorry.
There is a journal called Experiment in Mathematics.
There's a joke called experimental mathematics is, I think what's meant by that is something slightly different. Although, on some days, I will say what I do for a living is experimental mathematics. But what's at least used now is, you do numeric, typically, you do some kind of numerics. But I wouldn't object, honestly. I don't find that pejorative to be called an experimental mathematician. But my experiments typically, occasionally are numerical, but often other things. So, no, fair enough.
Okay, I think we should go for the reception, but thank you so much for